much.
Okay, please start with the last session, the national session. Okay.
Thank you very much. I would like to call the first speaker, Tatyana Mollayeva, with her team about the big data analytics to investigate health status transitions in traumatic brain injury. Welcome, and the podium is yours.
Hello, everyone. So I really wish I can speak Italian and understand everything that people talk about. It was really great to see slides. I'm Tatyana, affiliated with University of Toronto and Toronto Rehabilitation Institute, KITE Research Institute. We are from Canada, and as you can see on the screen today, I will be joined by Professor Michael Escobar, who will discuss results of our research that was funded by National Institute of Health. We will be talking about how we use big data analytics to investigate health status transitions in traumatic brain injury. Those were population-based studies, however, they are very relevant to what people who presented today do when they are dealing with individual patients in rehabilitation. So before I start, I would like to acknowledge the land on which University of Toronto and KITE Research Institute, Toronto Rehabilitation Institute operates. For centuries, it has been the land of Huron-Wendat, the Seneca, the Haudenosaunee, and the Mississauga of the rivers. Today, this is still a place for many indigenous people, and we are very fortunate to live and work in this land. So we do not have any financial or non-financial conflict of interest to disclose, but the research that we will share with you today has been supported by the National Institute of Health under award you see on the screen and partially by Canada Research Chairs. So why this topic is important, why big data analytics are important in traumatic brain injury. So for you who are dealing with individual patients, you may not see it so visually, but in fact, if you look at population or cohort studies, you see that to predict health status trajectories of people with traumatic brain injury, even within the same injury severity, is very challenging. Some people who are very severe recover very well, and some who sustain mild traumatic brain injury will experience prolonged symptoms and delay recovery. So we need to understand why this is happening. And to answer this question, we might be able to do with the help of big data analytics. So what is traumatic brain injury? Traumatic brain injury belongs to a category of acquired brain injury, and it is a complex and often lifelong process of alteration in brain function or structure or other evidence of brain pathology which has started with an external force. It's the event. However, this injury is not coming from birth, so it is not, in fact, congenital disorder, and therefore we can prevent this injury. And this is why we started to look into the data and the population of people who suffer traumatic brain injury. We want to prevent this injury and prevent the adverse courses of these injuries. However, traumatic brain injury is very complex. And as you can see on the screen, it has been recently established that traumatic brain injury can be a result of various pre-existing conditions which can modify the risk of injury. These include not only depressive, substance use, vascular diseases, and medication effect, but these factors intervene and intersect with other factors such as age, socioeconomic status, and often in non-linear manner. This makes a hypothesis-driven research in traumatic brain injury very challenging. And this is when computing techniques and machine learning might be helping us in understanding this complex injury and its courses. So the task, as said by Professor Escobar, who will present with me today, is possible by applying computational methodologies, and we draw our inspiration from genomics, so which allow us to test an association between thousands of bits of data to understand traumatic brain injury event. So now I will give a floor to Professor Escobar.
Sorry, I don't know if Professor Escobar wants to say something. I don't know. I don't understand.
Yeah, yes, he will be talking now, and I will share slides with you.
Okay. We are trying to activate his phone. Okay.
Thank you so much.
I think I'm on now, right?
Okay.
Thank you. No problem. Okay, so big data. We've talked a lot about big data in this conference. And it means a lot of things. Here's a nice reference we found that kind of put it in a nice little 3 V's. So big data refers to large data, which is unmanageable by traditional means. The 3 V's one can think about as volume, velocity, and variety. For us, though, I mean, we've thought a lot about things like velocity, where you have to get automatic feedback mechanisms and things like that. We've also saw variety when people are trying to take various types of data and mash them together. But where the real problem we have is volume. We have a large amount of data. So let me talk about our data environment on the next slide. So our study is in Ontario, Canada. And for people who don't know the structure of Canada, Ontario is the largest province, has about 1/3 the population of all of Canada. It's got about 15 million people. We're also a publicly funded university, so essentially everyone's healthcare is covered and is paid for by the government. Next slide. After a fair amount of work by some very forward-seeking people, about 30 years ago, they were able to convince the Ontario government that it was worthwhile to do research on this mountain of gold, which is the data they have. And this was an institution called ICES, which is a nonprofit institution which has ways of storing all this information. It worries about all the privacy issues. Can you hear me? We good? Okay, so it has all kinds of information about privacy. As the slide shows, there is roughly 18 billion lines of data. There are 750 billion different data points, 20 people, 15 million in the province, but that's total in any one time. That's moving in and out. Next slide also shows some of the repositories. So there are different repositories that are all linked. They're all secured. For our study, we were mostly looking at health services visits, which included acute care visits, stays, and emergency room visits. The information we collect from that is that we collect ICD-10 codes, which the CA stands for the Canadian version, but it's basically what everyone knows about. And we can find out who had a TBI by the codes they have. Next slide. So in our data environment, all the different types of data we are, this gives a lot of data opportunities for a lot of people, researchers in Ontario. So this covers basically the entire population, healthcare. What happens is that this leads to less differential access to healthcare. What that does is that lessens the selection biases that one gets when one is only looking at maybe one hospital or one health or one HMO or one health service unit or so forth. The other thing too is that since this is data sets, thank you for the opportunity. What we do is we have healthcare utilization prior to and post injury. So we collect all this information automatically so we can find someone who has a TBI. We can then backtrack 3 to 5 years or so, or even longer. We can figure out all the things that happened, all the times they used the services beforehand, and we could look post TBI, and we could look at all the things that they were using afterwards. Yes, so next slide, I think. So there are a lot of benefits to big data. There's also some problems. So for us, the real benefit here is that we can generate insight to the entire complex system. We're looking at everything. We're not just looking at, say, how does income affect TBI use or so forth. We're looking at everything in a very systematic way. We also have, since we have, did I say this already? Not yet. We also have greater power to see small effects and factors. So little bitty things that people may not see because they're rare-ish. We have a lot of people, so we can therefore catch it. Another benefit of big data, it's good for prediction. And also because of different tricks, you can therefore prevent overfitting. That brings us to some of the challenges of big data. So as a lot of people here may know, is that things, for instance, computational problems. Since large data basically gums up your machine and it doesn't work unless you have very clever algorithms. The other thing is that you have to worry about overfitting and overly flexible models. Otherwise, you get to see things like in one of the little graphs there, we look at just a general point cloud, but you can put a squiggly line, hit all the points, which no one really believes is true. Another problem is cursor dimensionality. That's something that is not intuitively obvious if you only live in a one-dimensional, three-dimensional world. Since we're looking at, like in our data set, we're looking at effectively 68,000 dimensions, things get to be very sparse and it's like the data really is a cloud. And the last thing that we have, the problem is difficult to interpret. So if you're just interested in prediction, that's fine. But for us, we're trying to actually figure out how this universe works. So having a black box is not exactly what we want. So therefore, we came up with some approaches, which is a blended method of doing things. Next slide. So basically, we took some of the wisdom that people in epidemiology and statistics have had. We've looked at people in the statistical genetics community, which basically has been a lab for where big data meets statistical principles meets real world problems. And so we steal some stuff from there, and we also borrow some stuff from the Barra statistical computing. So in classical epidemiology, for instance, we're looking at match case control studies, using some factors like that to control for various things. Classical statistics, a lot of the problem is because all the data is just so big, we need to crush it down and figure out what's going on by clumping it. So factor analysis methods, clustering techniques, there's a lot of work's been done in the last few years, but this work's been going on for about 100 years. Statistical genetics, there's things like multiple testing. You control for that using something called false discovery rates. And statistical computing, again, splitting data to protect for overfitting. We're also instituting methods like text processing, latent Dirichlet allocation models, and things like that, although not in this particular study. Next slide. So what is the population cohort we're looking at? So basically, we have people who have had about an 8-year window. If they've had a TBI in that 8-year window, they're in our study. So that encompasses roughly about 250,000 TBI patients is what we have. We're looking at each time they come to the emergency room or acute care, we're listing all the diagnostic codes. So acute care, we get 25 diagnostic codes fields. Emergency care, you get 10. We take the cohort, since we have so many people, we can split them into different splits, so we can therefore guard against overfitting and other problems with large data sets. And also we have a control groups come from the same data set. So therefore basically we have all this data. It's all very diffuse, very sparse, flying all around. It's very difficult to get a handle on it. So here's one strategy we've been using to try and do it, is we break it into these pieces, and the pieces look simple, but putting them all together is really the trick. So variable reduction, we have different ways of reducing the noise, looking for the signal and simplifying the data. We have to, because we're doing a lot of different testing, we have to have multiple testing correction methods. So we look at things like false discovery rate and things like that. And then next, what we do is once we have that, we take the patterns and we create patterns and clusters, and we then form. Sometimes we call this feature engineering. And finally, we try and visualize the data so we can get insights. So here's the next slide shows the a quick reduction of how we did this. So with ICD-10 codes, there are approximately 68,000 different codes. So the first thing we did in this particular study is we broke them into 3 character blocks because there's a certain hierarchy to these things. Then what we did was we looked to see which one of these variables had a signal. So we looked at 2,600 different McNamara tests, and we controlled for the overfitting by multiple testing by using false discovery rate methods, and that gave us 582 variables that seemed to have a signal. And then we crushed these down furthermore into 43 factors. So for example, the next slide shows for the preconditions, our first factor had those following variables. I can barely see them on my screen, but basically you take these variables, and these variables form a factor which we called cardiovascular disorders and other things. So that was one our variable. We had 43 of these things for our pre-injury case in this particular study. And I'll turn it now over to my colleagues to finish off. Thank you.
Thank you, Professor Escobar. So now I will tell you what results are and why we did this and what we observe. So really what we observe is that big data and big data analytics have a lot to offer to us because it helps us understand traumatic brain injury events better and also to understand transitions, health status transitions in traumatic brain injury and raise important hypotheses and important consideration for future studies to understand severity of injury and external cause of injury. So this is one of our study. So as the title suggests, data mining to understand health status preceding traumatic brain injury. So we apply this non-hypothesis driven approach to study health status preceding traumatic brain injury in comparison to people who use the same services, but for reason other than traumatic brain injury. As you can see on the screen, this odds ratio is factors preceding traumatic brain injuries that were associated with traumatic brain injury versus no traumatic brain injury. As you can see on the screen, sorted by effect size, factor top in the list, including those related to assault and child abuse, alcohol-related issue, adverse effect of medications and prescribed drugs, and occupational hazards in years leading to traumatic brain injury event. These factors suggest that everything should be considered in assessing patients' risk to traumatic brain injury. And they also point to complexity of social circumstances preceding traumatic brain injury event. Then we look at health status transition, how this health status preceding traumatic brain injury are reflected at injury event. Our results highlighted that health status transition in traumatic brain injury emerge in along projections of comorbidity, where many disorders, social and environmental adversities are reflected in external causes of injury and also injury severity. As you can see on the screen, the strongest association between health status preceding traumatic brain injury and health status at the injury event were between multiple body system pathology and advanced age-related pathology, which were strongly associated with false and severe traumatic brain injury. So why this knowledge matters? So this knowledge matters because we need to change our perspective to contextual injury event and recognize that health status preceding injury makes a person more or less acceptable to traumatic brain injury due to a specific external cause of injury and developing more or less severe traumatic brain injury. This entails new approaches to injury taxonomy, treatment, and rehabilitation, and also predictive classification. This is very important because it helps us to avoid transition bias, which can arise when people are prognostically different at injury event because of their health status preceding injury. So the result also acknowledge that we need to talk with clinicians, policymakers about this health status transition and in traumatic brain injury and other complex disorders of injury. What else we found? We have to look at sex-specific health status transitions because recent reports concerning sex and gender differences in TBI suggested that data captured in injury event might be differently shared between male and female patients. So we did so by using a Haddon matrix and classify the host, agent, and environment at injury event, traumatic brain injury event, and see differences between male and female patients. As you can see on the screen, we did observe differences, and this is not hypothesis-driven research, but data-driven research. For example, the strength of association between multiple system collapse in hospital diabetic and respiratory emergencies, septicemia, and severe traumatic brain injury were much stronger in male patients as compared to female patients, which may point to a more pronounced physiological dysregulation and biological vulnerability to early adverse effects after traumatic brain injury. So this is our study. We hope we shared with you enough information which you may be interested to read about how big data analytics help us to organize data in a meaningful way that we were able to make certain conclusions. Thank you very much. I would like to acknowledge our Acquired Brain Injury Research Lab and University of Toronto and funders who supported our research, and thank you for the opportunity to disseminate our results. Thank you.
Glinkowski? Wojciech? Glinkowski, please. Professor Glinkowski. Professor Glinkowski? Ok. Ok. È tutta ancora la linea? Ok.
Can you hear me?
Ok. Glinkowski, please.
Yes, can you hear me?
Yes, yes, yes.
Oh, that's great. I would like to ask audience, are there any questions to the presenters?
Thank you.
If we don't have any questions to the presenters, I would like to call Andrea Bandini to present a paper about the quantifying hand use in the home with first-person vision for individuals with tetraplegia.
Andrea?
Unmute yourself. Unmute your microphone.
No, no sé.
Can you hear me now? I couldn't unmute myself. Okay,
Yes.
can I share my screen? Oh, you should allow me to share my screen as well. Okay, there you go.
Okay, okay, Andrea.
All right, thank you very much.
Good.
So, can you see my slide?
Yes.
Okay, so good afternoon, everyone. I'm going to present some of the results, especially very recent results we obtained with the group at the Toronto Rehabilitation Institute, where, like the previous speakers, I've been working for the past 5 years now. I recently moved back to Italy, where now I'm working at Sant'Anna School in Pisa. But most of the results I'm going to show today were obtained at the KAI Toronto Rehab. In particular, I'm going to present.
Andrea, excuse me.
Yeah.
If you can share the other screen, because we are looking at the presentation.
Oh, sorry.
If you want, but
yeah, no, sorry. I was just sharing the screen and I didn't realize it was okay.
No problem, Andrea. You can go also because it's okay. It's the same.
Okay, let me try it again.
Okay.
Okay. Now, how about now?
Okay, thank you. Sorry.
Okay, perfect. No problem. So I'm going to show how we use computer vision for quantifying hand use at home in people with cervical spinal cord injury, in particular during activities of daily living. It's not okay. I don't have any conflict of interest to disclose. So upper extremity function in people with cervical spinal cord injury is one of the top recovery priority. That's intuitive because with our hands and our arms, we can conduct most of the activities of daily living. We can drink, we can eat, we can dress and feed ourselves. But there are some barriers that obstacle the optimal recovery of upper limb function. First of all, there are no outcome measures that are sensitive to the functional hand use at home, and in particular, motor improvement that are obtained in the clinics may not translate into an increased use at home. That's because we're lacking sensitive outcome measures that can measure how people use their hands at home. And second, patients are often discharged too early when they may still experience an improvement in their recovery. And especially in Canada, but I can experience also here in Italy, long distances between the home and the rehabilitation center make it difficult to accurately track the recovery when the patients return to the community. So this creates barriers to the optimal recovery and does not allow the clinicians to track how well people are recovering when they go home. So to propose something to fill this gap, we should propose outcome measures that could allow us to track the rehabilitation progress remotely, that can measure and that can be used for planning and validating interventions, and can be used for measuring an increased use in daily life, in particular as a result of a certain treatment and intervention, so that we can remove this gap and close this loop and optimize and personalize treatment in people with tetraplegia living in a community. So in the past, there have been many works on wearable sensors. For instance, one of the most popular topics is to use wrist-worn accelerometers. But the problem is that with these sensors like smartwatches and so on, we can just obtain global measures of upper limb function. So we're not able to track, for instance, finger movements and grasp, analyze the types of grasp when we interact with objects. On the other hand, there may be sensorized gloves that can provide more fine-grained information about hand and finger use. But in people with a reduced hand function and in particular sensation, these devices can be cumbersome. So in this context, in the past 5 years, wearable cameras that are usually worn on the head or on the chest have become popular as a candidate to obtain an ecological manner of recording activities of daily living and how people use their hands at home. Wearable cameras and egocentric vision have two advantages. First, the camera movements are driven by the user's attention. So in most of the cases when we are manipulating, we're focusing our attention and we look the manipulation area, what we're manipulating. And second, so we're recording exactly what we have in front of us. Being the only technology that provide not only information about hand function, but also on the context around the manipulation. For instance, what type of object we're interacting with and what type of actions we're carrying out. Of course, we need algorithms to exploit this information. And in particular, with computer vision and machine learning analysis, we were able to detect hand-object interactions and propose the basis to extract novel outcome measures of upper limb function. But in the past, the only results were obtained in a home simulation laboratory, the home lab at Toronto Rehab. which is a great simulation laboratory, but it's still a simulation apartment. So we have standardized light, same objects, same types of activities that can be conducted. So we lack the types of unpredictedness that we may have at home every day. So the objective of our work was to close the loop that I showed you before by using a wearable camera system that, by using artificial intelligence, could provide outcome measures of hand function in order to inform the clinicians on what was the recovery during activities of daily living at home. And in particular, we wanted to develop a wearable system that could capture information about functional use of the hands in individuals with cervical spinal cord injury living in a community. These specific objectives were to develop and test computer vision algorithms for detect hand-object interactions that, as I said before, are the basis for extracting outcome measures of hand function, and in particular to validate in activities recorded at home. And second, to extract outcome measures of hand function and validate them against clinical gold standards, in particular to correlate these outcome measures that I'm going to show you in a few seconds and see whether they correlate, and so they can be used in the future for measuring the quantity of a hand use. For this study, we recruited 20 individuals with cervical spinal cord injury. All of them were chronic participants, so they were they had an injury for more than 1 year. Briefly, these are the demographic and demographic characteristics. Just briefly, I mentioned that most of these participants had a cervical spinal cord injury, but had residual hand function. So we wanted to recruit people with not completely impaired upper limb function, because we wanted to record some activities to train the machine learning algorithm. So we wanted them to be able to carry out some activities on themselves. So the data collection was divided into 3 sessions. First of all, we asked them after the recruitment to come to the rehabilitation center, which is the Toronto Rehab Lindo Center, which is the biggest rehabilitation center in spinal cord injury of, I think, entire Canada, where we administered some clinical gold standard to measure the upper limb function, like the grasp. We measured the upper extremity motor score. We administered a SCIM questionnaire to measure the level of independence during some of standardized activities like dressing, feeding, and mobility. After that, we trained them to record some activities of daily living in an unscripted scenario. So basically, after a short interview with the participant, we try to understand what were the most suitable times of the day to record the daily activities. And we wanted to record glimpses of their daily routine. So we did not specifically focus on specific activities because we didn't want to stage them, but we wanted to capture whatever they were doing normally in their daily life. So for instance, over 2 weeks, we asked them to record a 3 session of 1 hour. And during that hour, they should do whatever they were doing normally. If they were cooking and preparing meal and have a dinner, they should record that one. If they were sitting on the couch watching TV, playing video games, they should record that types of activities as well. After the 2 weeks, they returned the cameras to us. We downloaded the video and we administer a short interview about usability and privacy perspective. We already analyzed these results, and for those who are interested about this qualitative analysis, you can read the reference paper at the bottom of the slide. So this is an example of how we recorded the videos. So we gave them a tablet so they could just press a button on the tablet, start the recording, and they were independent doing whatever they were doing normally. The camera was worn on the head with an elastic band. And as I said before, we wanted to record unscripted activities. So we just gave them time of the day, that we did not suggest what types of activity, as long as they could record activities that, of course, involved the use of the hands. After we recorded the videos, we analyzed this video with computer vision algorithms, in particular with a two-step analysis. First, we wanted to identify the hand location automatically using convolutional neural networks. And second, with the detected hands, we wanted to understand whether they were actively interact with an object for a functional purpose, in order to extract for each frame a kind of temporal profile of interactions. From this temporal profile, as you can see, this is an example of the analysis we conducted. So basically on the left-hand side, you can see the original video, and the right-hand side, you can see the analyzed video, where we could detect the hands, the object, the interaction between them. So we were able to analyze and identify the contact state between the hand and object, and understand, for instance, whether there was no contact, self-contact, contact with another person or with an object, either portable or not portable. To analyze to automatically identify the interactions between hands and objects, so we propose and implement different algorithms. Briefly, we use these algorithms based on convolutional neural networks to extract the presence of objects, hands, and their interactions. And we also try to do some adjustment, for instance, by analyzing the temporal information to see whether introducing a temporal information with a recurrent neural network could improve the performance. And we compared this algorithm with other two algorithms, number 4 and number 5, that we previously proposed and I presented in one of the past workshops of this group a couple of years ago. As I said before, after we detected the interactions between the hands and the objects, we could extract a temporal profile. And I want to spend a couple of minutes on this. So basically, for each frame, we could extract a 0 or 1 for each hand. And from this profile, we could we basically proposed these 3 simple outcome measures. The first one was the amount of total interaction time as a percentage of the recording time. So given a duration, for instance, of an hour, we wanted to understand what was the percentage of time spent using the hands for a functional purpose. Second, we wanted to measure the average duration of the individual interactions. And third, the number of interactions per hour. These 3 outcome measures were then correlated with the upper extremity motor score as a measure of the strength of the upper limbs, the skim as a measure of independence, and the grasp as a measure of strength, sensitivity, and prehension ability of the participant. I just skipped this. So basically, from the best algorithm, I just wanted to focus on the correlation analysis we conducted. So basically, these are the results that were extracted from both hands, the dominant hand and non-dominant hand. And we can see that both the percentage of time spent interacting with objects and the number of interactions per hour positively correlated, with correlations between moderate to strong with the UEMS and the skim. So that means that people with higher strength in the upper limb tended to use their hands for more time. And instead, for the number of interactions, people with, and we can see from the correlation with the motor part of the skim, with a higher motor ability, so more independent people tended to conduct more activities, more interactions. So that was the interpretation we gave to these results. Another thing that I didn't mention before is that we conducted these tests, this analysis, on more than 65 hours of video. Instead, the correlations with the unilateral outcome measures, with the unilateral gold standard, show similar results. So basically, we can see that the higher correlations were visible with the percentage of time and the number of interactions. In this case, we can see that most of the stronger correlations were more visible in the non-dominant hand. I mean, we're still trying to understand why this, but one explanation might be that people, especially in the chronic phase, may have recovered the use of their dominant hand. So they may, for instance, have they may use some compensation strategy to use their hands more. So in our opinion, the level of injury is less visible in the dominant hand, whereas this is more visible in the non-dominant hand. That's why perhaps these measures extracted from the non-dominant hand correlate more with clinical measures. In particular, we saw strong correlations with the prehension and the percentage. So basically, people with higher prehension that were able to manipulate with appropriate grasps the objects tended to spend more time interacting. And another interesting result was that especially for the non-dominant hand, people with a higher sensitivity in their hand tended to perform more activities. So basically it means that if people had a preserved sensation in their hands, they tended to do more activities. And this is quite interesting because we can see on the left-hand side that there are some weak yet negative correlations between the duration. That might explain this factor. That means that if people had a residual sensation, a preserved sensation, they could conduct more activities in less time. But it still needs to be demonstrated on a larger sample, of course. So in conclusion, we proposed some egocentric measures that correlated with clinic-based scores. In particular, the higher strength in the upper limb corresponded to higher interaction time, higher independence as measured with the skim to higher interaction time and a larger number of interactions, and stronger correlations with the non-dominant hand. So we demonstrated that using computer vision and wearable cameras are feasible ways to quantify hand use in a remote and ecological way in people with cervical spinal cord injury living in a community. We proposed the percentage of number of interactions as valid outcome measures for the amount of hand use at home. We wanted to move on, and future research we will try to link the quantity of a hand use, like in this case with these measures, with the quality of hand use. And when we talk about quality of hand use, what we'd like to do is to extract, still with computer vision, measures from grasp analysis to understand not only if a person is interacting with an object, but what type of grasp are they using? Is that the appropriate task for that particular object in order to inform the rehabilitation and personalize and optimize treatment in people with tetraplegia? So I'd like to thank the entire NET team at Toronto Rehab and all the members of this wonderful research institute that has been part of for more than 5 years. And of course, all the participants and family members who were part in the study. Thank you.
Okay, Andrea. Glinkowski?
Dr. Glinkowski?
Glinkowski.
Ah, okay. He's trying to interact.
Okay, Glinkowski is not here. We continue with the Professor Glinkowski? No. C'è una mano alzata. Some question? Chi è? Some question? No.
È lui.
È lui?
Sì. Credo che sia lui.
Sì. Glinkowski?
Yes, hello.
Okay, where are you?
Hello.
Continue.
I had to switch to another computer because I had a problem with the connection. Thank you very much. And I would like to introduce the next speaker. during our session. So the next speaker,
Beatrice.
Yes.
Beatrice.
Yeah,
The next speaker is
cervical dorsal roots to restore voluntary arm control in paralyzed monkeys. They are Beatrice Barra from New York University. Welcome.
Hi, thanks a lot for the kind introduction, and thanks a lot for the invitation to speak. I'm gonna try and share my screen. Oh, sorry, apparently I need to. Okay. And so unfortunately, I cannot share my screen unless I leave this meeting and then rejoin. I don't know exactly for which reason, but my computer is complaining. I'll be back in 1 second.
Okay.
Sorry.
Don't worry, no problem. È imbostata come relatrice? So we are checking if you have the rule of presenter. Maybe that's the problem. Let's try again.
I'm gonna try again. It looks like I can now. Sorry for the glimpse. I don't use.
Okay.
All right. So now you should be able to see my slide, and you can let me know if you see it fully. All right. So as I was saying, thanks a lot. Sorry for the small waiting. And I'm very glad to present to you this work about how to use electrical stimulation of the spinal cord to restore upper limb function in case of cervical spinal cord injury. So I, just because probably lots of you don't know me, I have actually studied in Milan, in Italy, so I'm particularly happy that when I have the chance to talk to an Italian audience. And then I moved to Switzerland, where I, under the supervision of Dr. Marco Capogrosso, I have done this work that I'll present to you today. And then I moved on to the University of Pittsburgh, and then afterwards to NYU Grossman School of Medicine, where I am now. But all the work I'll present today will be from the work I've done with Dr. Capogrosso in Switzerland. I have a conflict of interest to disclose because we have produced this patent. That's the only thing that I need to disclose, and I'll dive directly into it. So I'll talk mainly about the clinical focus, which is cervical spinal cord injury, which is a condition that usually strongly impacts patients that are affected by it because it usually causes tetraplegia, so the complete loss of control of, not complete, but the loss of control, at least partial, of arm and hands. And these cases usually amount for at least half the cases of a spinal cord injury. To this day, the most used clinical applications rely to functional electrical stimulation, so the direct electrical stimulation of muscles in the arm and hand, which is a technique that has done great and it's very well used, but it's particularly functional for patients that have mostly grasp impairs, but it's very difficult to use for patients that have a full arm impairment because by directly stimulating the muscles, it is very easy to cause muscle fatigue. And so this basically prevents patients from supporting the weight of their arm for a long period of time. And also because the number of muscles in the arm and hand is very high, it is very complicated to architecture and orchestrate all the different activations of muscles during a very high number of arm and hand movements that we usually perform during normal day life. One other strategy that can kind of come in help after FES is epidural electrical stimulation. So basically this stimulation of the spinal cord on its dorsal side in the epidural space. This electrical stimulation technique, differently from functional electrical stimulation, does not recruit directly motor neurons, so motor fibers, not muscles, but recruits sensory fibers that then synapse to motor neurons in the spinal cord, and so activates motor neurons presynaptically. And this has the advantage of avoiding muscle fatigue, because motor neurons are recruited through their natural synaptic connections. So the activation of muscles results more natural, and it's easier to produce a weight-bearing activation of these muscles. This technique has been used successfully to restore locomotions in a variety of animal models, and finally also in patients. This is a figure that has been extracted from a paper from Wagner et al., in which this technique has been used on the lumbar spinal cord to basically reproduce the normal pattern of locomotion. It has worked very nicely because it's a very simple technique. It's quite robust. It's very easy to customize it to the needs of the patients. However, the problem that we were facing was to translate this from locomotion to the upper limbs. And it's quite a challenge, because locomotion is a movement which is quite repetitive, it's very standardized, it's unidirectional. You can assume that if you find a good solution for a patient for a normal walking pattern, then it's gonna work over time very well. However, for upper limb movements, that's not the case, because we can do very different movements in a non-repetitive manner. The onset is not necessarily very easy to understand. Different movements have very different muscle activations. So to open a drawer, lift a cup of coffee, you use very different muscles in a very different way. And it's a movement that happens in the three-dimensional space. So you have to account for a lot of directions. And so we have structured the project in order to trying to solve these main challenges in translating this technology to the upper limbs. First of all, we had to design a platform that could allow us to study these the complex arm and hand movements in non-human primates, which is the only clinically relevant model for this type of injury. Then we had to design a spinal interface, so an electrode that could help us to actually achieve very complex arm movements, design a stimulation protocol, and also test its efficiency. So first of all, we have designed this platform. As I said, we have used non-human primates as a model because they have an anatomy which is very close to humans, and also a functional use of the arm and hand, which is basically the closest to humans. The animals were faced with 7 degrees of freedom robot. So they had to interact with the robotic arm in order to complete the task. And especially they were instructed to reach for the end effector of the robot that had a specific object on its tip, reach for it, grasp it, and pull it towards themselves until it's predefined threshold in space. And we designed this task very carefully in order to account for different factors. First of all, we wanted the movement to be three-dimensional, so really to happen in the 3D space. We wanted it to be the combination of different basic movements that underlie most tasks in daily life. So reach, grasp, pull. If you try and deconstruct any movement that we make with the arms, you can kind of refer it with these three phases. We wanted it to be fairly standardized, so that's why we decided for robotic tasks, so that we could always reproduce a very similar task. And we wanted it to be against the gravity, because we wanted to test whether stimulation could help us to make them support the weight of their own arm. And while the animals were performing this behavioral task, we could record a high number of different signals from the animals. First of all, the intracortical signals from motor, sensory, and premotor cortex through electrode arrays. And then we use these intracortical signals to deliver stimulation on the spinal cord. We could record the kinematic signals through a Vicon motion capture system, as well as the force of interaction with the robot and the activation of 8 different muscles in the arm and hand. Second major step that we had to do was to design a spinal interface, as I said. And so to do this, we basically went back to the anatomy. This figure is actually a remade version of a figure present in a paper from Jenny and Inukai that have studied the anatomy of the cervical spinal cord. You can see that this is basically the distribution of the innervation of the different muscles across the different segments of the cervical spinal cord. So you can see that while there is not a very precise mapping between the segments and each muscle, there is somehow a broad organization of these, we call them motor pools. So we basically designed our electrode to cover all this region, and we included different contacts so that we would be able to stimulate different segments of the spinal cord and so to target different muscles. We also developed a robust implantation technique so that we could implant this electrode in 3 different animals in the same position with the same procedure. And we personalized the size of the electrode and the design of the electrode on the specific anatomy of the animals. So we took CT scans of the different animals. We measured the width and height of the spinal canal, the length of the cervical segments, and then we scaled up and down the electrode so that we could target precisely the different roots. Once we have done this, we checked that we actually could elicit muscle activations in a selective manner so that we could stimulate from different contacts and activate different muscles. And what you see here is what we call in our experimental language recruitment curves. So we have delivered pulses of current from different electrodes. Here's from electrode 1, 4, and 6, which are basically ordered rostrocaudally, at different currents. And we have recorded the muscle responses that follow this stimulation. And you can see that by stimulating at these 3 different contacts, you obtain an activation of very different set of muscles. So by stimulating rostrally, you activate mostly deltoid and biceps muscles, so shoulder and flexion, strong flexion muscles. By stimulating a bit in the middle, you activate extensors mostly. And by going even more caudally, you activate wrist and arm and hand muscles. And this was the case for all the 3 animals. We then try and check whether we could then deliver trains of stimulation, so not single pulses of stimulation, but stimulation that could allow for smooth movements over time. And what we found is that actually the mapping was conserved. So every time we stimulated rostrally, we caused an elbow flexion. Every time we stimulated from the middle of the electrode, we caused an elbow extension. And every time that we stimulated caudally, we had an hand flexion or wrist flexion. And here you see basically the representation of the stick diagram of the arm as defined on the drawing. And you see how it changes during the stimulation burst. We have also tried to modulate the frequency of these stimulation trains, and we have found that by changing the frequency of the stimulation, we could change both kinematics features. Here you see the elbow extension angle that you can obtain by changing the frequency of stimulation, as well as the activation of different muscles. So you see that here in blue, you see the activation of the triceps muscles, and you can appreciate how it changes by going higher in stimulation frequency. And the same results we obtained with the extension, even though I have to mention that for all the muscles that were more related to arm and hand function, we have figured that by going too high in stimulation, this effect was lost. And I'm happy to discuss about this particular effect if anybody has questions. Once we figure out a little bit what we could do with our electrode, we then designed our final stimulation protocol, the one we wanted to use during the behavioral task to help the animals once they had the injury to recover their functions. And so to do this, we kind of, we knew we had to we merged together 3 different phases, which are the phases of our task: the reach, the grasp, and the pull. And then we wanted to select the optimal frequency for our stimulation. We used a combined measure of how much we could activate, how much we could produce a movement. So what was the kinematic output of our stimulation burst, and what was the smoothness of this movement. And so we concluded that by using very low frequency, the smoothness was very nice, but actually the movement produced was almost non-present. So we discarded this frequency range. However, by going very high, we had a very good movement produced, but a very low smoothness. So we discarded these 2. We choose a middle ground, 50 Hertz, which is actually something that has been used clinically very efficiently as well. And so our stimulation protocol is composed of 3 different bursts: 1 to create reach, 1 to create grasp, and 1 to create pull, all of them at 50 Hertz. Here I can show you very briefly a video of the different movements that were created by stimulation in anesthetized condition. So all of these, the animal is asleep, they don't know what's happening, and we stimulate it from different contacts. Here's what happens when you stimulate from a very rostral contact, so activate basically a shoulder movement. Then when you stimulate around the C7 segment, you basically create an elbow extension. And by stimulating more caudally, you can create a hand flexion without any other movement occurring at the same time. Actually, there's one other thing that I wanted to share. If you chain these 3 types of stimulation together, you see that you can achieve, even in anesthetized conditions, something that looks like a reach, grasp, and pull. And so this is exactly the stimulation protocol that we wanted to then reproduce in behavioral conditions. Oh, sorry. Voilà. So once we had our stimulation protocol developed, we then had 3 monkeys with a cervical spinal cord injury. You can see that the extent of the injury, that it's marked in dark for all the 3 animals, it's quite different. So we had an animal that was very, very impaired, and other 2 that were a bit less impaired. Those are lesions which are performed surgically, but it is also very difficult for the surgeon to reproduce a perfect lesion. And then in these 3 animals, while they were performing the task, we analyzed how stimulation facilitated muscle activity, how improved task performances, and how improved the overall quality of the movement. I'll start from the muscle activity. You can see already qualitatively from this graph that while with stimulation of the monkeys after injury were not able to produce sustained muscle activity, with stimulation on, this comes back. So the muscle activity is much higher. And this was consistent across all the 3 animals. And I would like to underline here, highlight that these are experiments performed 6 days after injury. So there's really no chance of recovery for them. They're barely starting again to be able to stay in the chair, perform the task, and feed themselves, etc. Then we also looked at how stimulation improved task performances expressed as the number of movements that they could perform per minute. Here you see, I would like to focus especially on these 2 animals because this one was very impaired. So we always only performed reach task, not grasp and pull. You can see how the task performances for stimulation and non-stimulation evolve over time. You can see that there is a general improvement even without stimulation due to time. These are lesions that allow the animals to recover some of the function anyway. But you can see also how stimulation each day improved the general performance of each animal. And also it is interesting to see how, depending on the amount of lesion, which was different from the 2 animals, stimulation really impacts different functions at different time scales. So for example, this animal, which is less impaired from the beginning, has a very moderate recovery during reach, because reach is already quite good, but it has a huge improvement in grasp and pull function from the beginning. While this animal on the top that was more impaired at first an improvement in the reach phase, and the improvement in the grasp and pull function come much later in time. And then we also looked at the overall quality of the movement during stimulation and non-stimulation. And here, to do this, we basically computed a lot of kinematic features, and then we performed a principal component analysis. You can see in this graph a representation of how the different movements in the three different conditions organize over the space. The gray is everything before the lesion, so the normal movement performance during the task. And then you can see that after lesion, the black dots are quite far in the space from the gray dots. But when we perform stimulation, which is the blue dots, while it doesn't get back completely to the original state and the original movement performance, it gets an improvement in the right direction. So it places themselves exactly in the middle between the lesion state and the intact state. And if you look at different features, which are key features in movements for these animals, you basically see a very similar story. So if you look at the elbow height for this animal, for example, the gray is before lesion, there is a general average height at which she keeps the elbow, and after injury, she's not able anymore to really keep her elbow up, so she kind of drags the elbow all the time. And with stimulation, she's able to bring back the elbow at a very specific height, which is very close to where she had it before. And same goes, for example, here for another animal, for the force applied on the robot. You can see she had a quite acceptable level of force. Actually, this data has been normalized on the original level of force, median level of force. You can see the drop after lesion and the recovery with stimulation. Here I have a couple of videos just to show you a little bit when we did the experiments, how did this look like. You see this animal is the most impaired one, the one that did only reach. You can see that the arm, which is highlighted here by this white stick, it's basically unmovable. The only thing that she can do a little bit is to flex it, but she's trying to extend it to reach this object, which my colleague is presenting to her, and she doesn't manage. And when we delivered stimulation, she actually, in a bit shakily, reached for the object and extend her arm. Here, there's another example of the same. And I have another animal to show you which performed instead the pull, to show two different movements. So this animal is the least impaired, the one I told you that could kind of reach at all times. So you see that even without stimulation, she can reach the object, and then she stays on the object because she cannot grasp and she cannot pull this robot. And you'll see in a second what happens during stimulation. You can really appreciate how she manages to grasp and pull at the exact moment in which stimulation is delivered. You can control the stimulation here downstairs. Voila. And you can see a subsequent one. So this was our main result. And then one last thing that I wanted to highlight for you, which I thought was very interesting, is that we have looked a little bit of what was the interconnection between the stimulation, which was delivered artificially by us, and the cortical control that, of course, remained intact after spinal cord injury. So we, as I told you before, we had intracortical recordings from 3 different areas. So we have looked in the motor cortex what was happening while we were delivering stimulation. And we found that there were basically 2 cases. There were cases in which we were delivering stimulation, but we did not notice any really evident cortical activation, while there were cases in which while we were delivering stimulation, we also had a consistent cortical activation. And we have noticed that in most of these cases, you would have no movement while you didn't have any cortical drive, and you would have a movement while you had cortical drive. So we have looked at this in depth. We have generalized for basically all of the neurons that we had, and we found that there was actually a trend. So every time that there was a clear distinction between the cases in which we deliver stimulation and the monkey did move or didn't move in the neural space. And this was statistically significant for both animals in which we looked at this thing. So we actually hypothesized that this was a very interesting effect of the cortical control, residual cortical control, acting as a gate for stimulation. So enabling or disabling stimulation at times. So in conclusion, we have personalized an implant to try and allow for independent stimulation of different dorsal roots. We have checked that epidural electrical stimulation of the dorsal roots can produce single joint movements, and that we can use this type of stimulation to restore arm and hand movements after spinal cord injury. And we also have observed a very interesting effect of the fact that the stimulation and residual cortical control need to be somehow in tune for the stimulation to have an effect. And with this, I am concluded. I would like to acknowledge especially Marco Capogrosso, which was the leader of this project, and several colleagues of mine, Tara, Matt, Marion, and Katie, who has worked relentlessly at this project, as well as many other people that were somehow involved in this very big and long project. And I thank you very much for the attention and for the opportunity to present this work.
Professor Glinkowski? Grazie Beatrice. But Glinkowski is orthopedic professor. One question to Beatrice? Yes, okay. Professor Milia, Director of Neurorehabilitation in Prosperius Institute of Rehabilitation.
Thank you, Beatrice, for this kind presentation. It was really impressive. Thank you very much. But I'm really interested about, because I am a neurologist, so to reach the movement after electric stimulation can also be presented as a reflex, okay? But pull is obviously a normal movement, a voluntary movement. So how can be done the tune between the cortical control and electric stimulation?
So that's a very interesting question, probably the most interesting of all for clinical applications. So thank you very much for asking it. So what we figured, even though I would say this is probably the part of our study that was the most hypothetical, we didn't really have the data set to dive deep into this. Our hypothesis, what we have observed, is that it is really not necessary for the scientists to tune this necessarily, but it's the brain that does this autonomously. And the way that we think this happens is through presynaptic inhibition or cortical modulation of 1A sensory fibers. So as you said, this effect that we are actually generating is a reflex. It's basically, those are the fibers that are responsible for the reflex. So we are exploiting a reflex circuit to generate movements. And what we think is happening is that the brain has control over these fibers. So the brain has still some residual control over some of these fibers and can say, well, these I really want it to happen, or these I don't want it to happen. Like my aim is something else. So one other thing we have observed, for example, is that we had cases in which we stimulated with the wrong stimulation, let's say, like we were stimulating flexion during extension or extension during flexion because of a mistake in the timing or anything like this. And we have looked at this data, and what we have found is that while there were some, while the animals kind of felt it as an additional difficulty, there was never an uncontrolled movement generated. So it's not that if we generated a flexion stimulation protocol, the animal had to flex. The animal could block this movement if it was not their intent. So our conclusion is there's really some residual cortical mechanisms that regulates reflexes. Does this answer your question?
Yeah, sure. So this means that the monkey got the idea of movement and the electrical stimulation gives him the way
Yes.
to realize the idea.
That's exact. It's like giving him power.
Perfect. Thank you very much.
Thank you. Glinkowski, Professor.
Thank you for the very interesting presentation. Are there any more questions from the audience?
No.
So thank you very much. It was very interesting. I'd like to call the next speaker, Matteo Malosio and Matteo Lavit Nicora, and to present the PhiCube, the robotic device.
Chi c'è? Matteo?
Sì.
C'è Matteo Lavit? Just question, vediamo se c'è Matteo. Abbiamo abilitato? Sono due Matteo, o Malosio o Lavit?
Yes.
Scusate, penso che debba essere, io sono Matteo Malosio, credo che debba
Matteo.
essere tolto. Ok, ce l'ha fatta, ok, scusatemi.
Prego.
Grazie.
Prima Matteo Malosio. Ciao Matteo. Ok.
Ok, buongiorno a tutti. Condivido lo schermo.
Okay. Poi sta usando la...
Can you see? Ok.
Ok.
Right. Okay, good afternoon, everyone. My name is Matteo Lavit Nicora. I'm a researcher at the STIMA Institute of the National Research Council of Italy. Today, together with my colleague Atul Chowdhury, I'm here to present to you PhiCube, which is our last born project in the field of telerehabilitation robotics. First of all, just a brief overview of the world we are picking into today. As you know, neurological disorders represent a worldwide problem with great social and economical impacts. Neuromotor rehabilitation is therefore extremely important to promote motor and cognitive recovery following events such as stroke or cerebral palsy. In order to maximize the effectiveness of therapy, the development of upper limb rehabilitation robotic solutions has to lay its grounds on a series of fundamental aspects. First of all, the complexity of movements and motor coordination must be taken into account throughout the whole development process. Moreover, low intensity treatment or limited active engagement of the user can negatively affect the recovery process. For these reasons, we propose PhiCube, which is a friendly robotic device for bilateral upper limb domestic rehabilitation. Our solution is capable of adapting to several upper limb movements. It's portable in order to accompany the patient even outside the clinics, and entertaining to promote active participation of the user during the recovery process and therefore facilitating neuroplasticity. In this slide, you can see our current patent-pending PhiCube prototype. It's, as you can see, it's composed of a central motorized unit, which is connected to a mechanical adjustment system and to a series of configurable accessories. And on top of this, a number of hardware and software solutions are offered to provide high levels of flexibility while keeping the device as compact and portable as possible. Here you can see a series of functional movements which are made available by the device and useful in the context of upper limb rehabilitation. Starting from its first development stages, PhiCube has been designed as a polyfunctional modular device capable of hosting a rich set of accessories in continuous expansion. So the cool thing about this is that With a single central body, it is possible to generate a wide range of movements, bringing personalization and usability up to where they can meet and satisfy both the therapist and the patient's needs. So in this slide, you can see a video of our first version of PhiCube, but I still think it's very useful to let you better understand the flexibility and intuitiveness of the device. Just as an example, here you can see my colleague, Davide, quickly reconfiguring the device to switch from a bilateral lever action to a well-known steering wheel configuration while playing along with some entertaining virtual environments. Using this first prototype, we also ran a first usability and acceptability test during the summer camp organized by PhiCube organization. And this was a great opportunity for us to collect initial positive feedback, both from children with cerebral palsy and from therapists and caregivers that were attending the event. In this occasion, the adaptability of the device was extremely useful in accommodating all the ergonomic needs of the patients. And to our surprise, it didn't take long before a line of kids waiting for their turn to interact with PhiCube was formed. So, and this is the enthusiasm that is still keeping us working on improving the device. From a more technical point of view, the electromechanical compartment of PhiCube has been specifically developed to constantly monitor the forces exchanged with the user. And thanks to this solution, the control architecture is capable of understanding how the user is interacting with the device, and therefore assisting the patient throughout all those movements that cannot be correctly performed autonomously. Moreover, past and current performance data are actively exploited to adapt the level of provided assistance so that the proposed rehabilitation exercise is always characterized by a suitable difficulty level and therefore useful for neuroplasticity and motor recovery. Functional requirements are the main drivers for the design of PhiCube's hardware and software solutions. So thanks to two actuated axes and the proper control logics, the device can be configured to support the two upper limbs individually, defining the level of assistance necessary for each one of them on the basis of the task to be carried out and the patient's residual mobility and performance. On top of that, the bilateral architecture that characterizes the device allows for a coordinated assistance action, which is particularly useful for hemiplegic patients, since in this case it's the healthy limb, which is still capable of correctly performing the movement, that is directly assisting the plegic limb through the process of motor and coordination recovery. That said, there are a few reasons why we believe that this kind of solution is perfectly fitting the current situation. First, telerehabilitation and telemedicine markets are rapidly expanding, and also recent clinical evidence shows that rehabilitation can lead to important results even in the chronic phase, when the patient is normally going to the clinic much less frequency, if at all. And finally, the advent of 5G technology and also the recent pandemic that we all experienced have caused a strong acceleration of solutions targeting the world of telehealth. So now, before going into our future technological roadmap, I will ask the help of my colleague Atul, and we will try to give you a live demo of the device, if technology assists us. So I hope you can still see my screen, and right now you should be able to see. Okay. Right. So I hope it's not too shaky. I will try to be steady. So here you can see the first version of the prototype, which was the one that you saw in the videos that I showed, and also in the usability test that we ran at the summer camp. Well, here you can see the whole set of accessories that we have prepared and that is in continuous expansion. And here instead is the new prototype, which has been improved both in terms of design and mechanical and electronic performance. So you can see my colleague is using basically this mechanical adjustment system to change the orientation of the cube and therefore the orientation of the motorized axis. And this allows us, together with a set of accessory, to perform a wide range of motion and of movements with a single device that is just, as you can see, clamped to a regular table, equipped with an emergency button, and comes together with an application that we developed to basically interface the rehabilitation device with just some serious games that can provide entertainment during the rehabilitation sessions. So maybe if we can now, Atul is going to show you the setting of the device, so we can just load the setting that we required for the specific training exercise that we want to perform. And now we can attach the corresponding accessory that we like. In this case, it's just a steering wheel. You can see it's just a screw mechanism that allows for the connection of the accessory to the cube. So this is an example of a game that we prepared to use the steering wheel. Of course, it's a racing game, and you can see that in this case, my colleague Atul is playing with the device. We have some feedback both in the form of lights and of audio, but I'm not sure you can hear it right now. And the device right now is giving just resistance to the user. So as you can see, there's a spring back to an equilibrium position. Now maybe we can show a different, like a reconfiguration of the device. And very quickly, just by, we can stop the game, and just by changing the set of accessories that are attached to the cube, we can change completely the exercise and also the functional movement that we are rehabilitating. Now we're going to show you wrist rehabilitation exercise. We will use this second set of handles, which is basically reproducing what would be like a motorbike gas handle. So right now we have the motorized axis coming out from the sides of the cube. And very quickly change again the setting of the device to behave as we desire. We have a set of predefined settings, which can always be expanded and tuned according to the patient that is using the device. Okay, so attaching the handles. And maybe in the meantime I can set the game. Okay, in this case, this is a second game that we are just proposing. It's the goal of this game is to move the red capsule in the environment to get some targets, and this is done with the asynchronous motion of the wrist. In this case, again, the wrist is given some resistance from the device, and the motion is correctly executed only if it's asynchronous. So you can see now gameplay running, and yeah, so targets, you can see feedback both in the form of sound and lights. And in this case, you can see the motion is on the wrist, and we are giving resistance to the patient. While maybe very quickly we can show a last exercise in which just using the same handles but reconfiguring their orientation. So rolling. Okay. Yeah, in this case, the game is just basically a rowing game. We have a canoe going through a river, and the movement that has to be performed in this case is a synchronous movement. It's a synchronous movement.
Si capisse per esempio la velocità di quella pallina si poteva regolare oppure addirittura si poteva
second. Right, so you can see that the handles are being reconfigured right now, and the gameplay can start. So in this case, the device is set as a bimanual assistance logic. You can see right now, basically one hand is driving the other one. Suppose that one hand is the healthy one. You will assist the pledged limb in the motion. Of course, the level of assistance can be regulated according to the patient's needs. And finally, maybe we can show last configuration, and then we just briefly wrap up this presentation with our future works. In this case, we are changing the device to have two different handles on the two sides, performing two different kind of motions. So this is also trying to rehabilitate coordination and giving some cognitive tasks to the user to be performed. You can see now what we call a crank handle being connected to the device. In this case, we don't have a spring back to an equilibrium position, but the handle will be continuously turned. And the game is a virtual environment exploratory game where some targets are provided to the user. And okay, so you can see in the environment there's this the avatar moving around. One hand is controlling the rotation, the other hand is just controlling the back and forth movement to move around the virtual environment and go grab some targets that you can see as a light of column right now on the screen. Okay, and finally, all the data that are being collected from the session are logged continuously. So data is logged both from the use of the device and the performance during the game. And we provide a preliminary data report which selected the user, the specific session that therapist, for instance, is interested in. We have basically a summary of which games have been played and the percentage of time they were played. And then here you can see just a quick example of the movement performed during the task by the user that were logged during the therapy session. So right now, I will just switch back. I will switch back to my presentation. Okay. Right, so you have just seen PhiCube at its latest development stage. We are constantly working on the improvement of usability and functionalities. And in this process, we are paying particular attention to the reliability of the device together with its modularity, which will allow us to keep introducing new features in the future. Our goal is to have a certified product ready to be offered to the market by the end of 2023. And after that, PhiCube will be interfaced with existing telerehabilitation platforms in order to both allow the clinics to receive and monitor data related to the patient's performance progression and to offer live therapy sessions using a webcam and directly connecting with the remote professional. We also intend to focus on the empathetic and social interactions capabilities of PhiCube. So using the previously mentioned integrated webcam, the device will be able to analyze facial expressions in order to infer the patient's emotional state. And then all of this information will be expanded by physiological data measured by a non-invasive wearable device, such as a smartwatch. Thanks to this dataset, we intend, of course, appropriately protected. We intend to use artificial intelligence techniques that will be in charge of tuning the behavior of the device in order to mitigate any situation of stress or boredom that may negatively affect the outcomes of the therapy. And finally, I want to thank all the PhiCube team without which this project would not be possible. And of course, all of you for listening and for giving us the opportunity to present our work. So thank you very much.
Okay.
Glinkowski.
Professor? The audio is switched off. I don't know if...
I'm on.
Okay.
I'm on there. Thank you very much. Very interesting device, very progressive, and I think it will have a nice future. Are there any questions to the team of developers of the PhiBox at the moment from the audience?
I have only one question. I don't know if it can make sense. I'm Luigi Pavone from Neuromed. Maybe I don't understand so much. For example, the velocity of the ball, the red ball in the game you showed us, it is fixed. It can be set up by the operator, or otherwise is modulated by the patient conditions. I mean.
Yeah, so yeah, I understand the question. Thank you for it. Of course, the device has been thought to be as much like to offer as much personalization as possible. So right now, both, let's say, the rigidity or the level assistance or every configuration of the mechanical device is free to be tuned by, I would say, the therapist. And also for the game, I didn't show it very well, probably, but every game has a game-specific related setting interface, where, for instance, you were mentioning the sphere game. In that case, we could regulate the speed with which the ball would go forward, so the movement that was controlled by one of the hands, and the speed of rotation independently and freely as desired. Of course, the goal in the future is to have all these parameters automatically adapting depending on the patient's performance level, residual mobility, stress level, as I said, and so on.
Okay, thank you.
Thank you very much.
How do you have solved the problem of gamification and, let's say, the interrelation with other players, if there is any possibility to join other people and check the results and share the results with other people or with social media or something?
Yeah, so thanks a lot. This is a very nice future work for us. It is not implemented for now. But of course, gamification is very important for us. We are mainly targeting children, which are becoming closer and closer to social networks, social media. So that will be definitely a way of expanding the functionalities of the device. Right now, everything is running on a local system, and it's a single-player system. But this is just basically a first prototype of the device, so we have a long way to develop the system. And thanks a lot for the suggestion, which is a great suggestion, I believe.
Thanks. Good luck with your device and the system.
Thanks a lot.
Are there any more questions from the audience?
No.
No more questions, so then I would invite the next speaker. Our next speaker from Palestine. Yes, that's wait a moment. It's Asma Hassan Sbai. And The podium goes to Asma.
Oh, it seems that she's not
with us.
It seems Renzo non c'è. Maybe she can raise her hand virtually in order to understand if she's online, she's with us. Because this morning we saw her online, so probably it's too late. we are a little late. So, I don't know if it, non c'è niente in chat. I don't know what to do. Professor Sicurello is trying to send an email to her, or maybe a WhatsApp. It's faster. No. We are trying to contact her by WhatsApp. Otherwise, we can maybe hand. I don't know, Professor.
Okay. Maybe Asma is not connected. She's PhD in neuroscience imaging. I don't know, because today, this morning, this afternoon, she was here in connection. Asma? No. Okay, Professor Glinkowski, you can conclude and I don't know if our neurospine symposium we can organize in your country, because it's very. What is the situation now in? Is quiet or not in your country?
Well, it depends what we mean. If we would discuss about the Ukrainian situation, that is the quiet situation. We don't have any particular problems with that. We have a lot of refugees from Ukraine.
Yes.
However, this is really quiet and everything is solved, I think.
On the next week, we can discuss about the organization of a neurospine workshop in September, October, or when the situation, I don't know. Okay, we can conclude this session. Asma is not here? No. Thank you, Professor Glinkowski. Thank you all the speakers of this international session. Thanks. Ciao, and we see in another occasion of. Maybe we ask you the organizer the slides in order to put the slides in our website of Neuromed Institute here in Molise in Central Italy. Thanks again. Ciao. Bye.
Thank you very much. Ciao.
Thank you, everyone.
Thank
Have
you.
a nice day. Ciao.